Welcome back, students. In this video, we're going to cover lesson 3-5. This is proving segment relationships. See the standard below the title, GR1.1. I'm going to start with a couple of postulates and a theorem, and then I already have the vocabulary written there, but I'll do all this and we'll move down. So, excuse me. Starting in the left corner, so postulate 3.8 is called the ruler postulate. So you see a ruler down there. The points on any line or line segment can be put into one-to-one correspondence with real numbers. So example is any 2 points AB on a line. If A corresponds to 0, B corresponds to a positive number. And what they're telling you, and if you've ever used a ruler or a tape measure or any measuring device, there are no negative measurements. When you're measuring something, it has to be positive, and that's really what that whole postulate is about. So just remember that your variable can be negative, but the actual measurement of, say, line segment AB or whatever, it has to be positive. Okay, moving forward. All right, to the right. So over here, the segment addition postulate. All right, so if A, B, and C are collinear, then point B is between A and C if and only if AB plus BC equals AD. So anytime we're adding line segments now, not just adding. So we're going to do proofs, and there's going to be times that your equation is going to call you to add, and it's going to be the addition property of equality. But when you're speaking specifically of line segments, so we'll say that AB is green, and we'll say, we'll do red, that's fine. BC is red. Okay, so where's my other colors? Apparently all I have left. Oh, here's the blue. Okay. So AB plus BC is going to equal AC. AC is the whole line. So your green plus your red equals the blue. And, when it's a line segment like this, so segment AB plus segment BC equals segment AC, it's always segment addition. And remember, so B here is in the middle, so AB, BC, your B's are facing each other. Well, that's because B is the point in the middle of these two. Not the midpoint, but a point in between there, or a point in the middle. Okay, I'm going to go below here. So the properties of congruence. So we have line segment AB. And we can say that line segment AB is congruent to itself. That's something for later. We're going to have triangles that share a side. That side has to be congruent to itself to prove the triangle congruency. But for now, just know that AB is congruent to itself. If you look in the mirror, you're going to see your reflection. People like to say the mirror makes them look bigger. But unfortunately, no, that's not true unless it's a special mirror. So what you see is what you get. This guy is congruent to himself. And I say mirror because I like to reflexive. You reflect in the mirror. All right, so line segment CD. All right, so symmetric means we have two, that if this is equal to this, then you can say it the other way. A good example also is, say, if 2 plus 1 equals 1 plus 2. So think of it in that way. 2 plus 1 equals 3, and 1 plus 2 equals 3. 3 still equals 3. So this guy, if this is congruent to this is congruent. They're back and forth. And then the last one, so the symmetric. The transitive. Sorry, I can't talk. So it says if this guy is congruent to this guy and this guy is congruent to this guy, then the first and the last have to be congruent. They're both congruent to the guy in the middle. And that's what it says here. If AB is congruent to CD, CD to EF, then AB has to be congruent to EF. The example we used in class was, if you know that me and two of the other students, I named folks in class, but if the three of us have the same amount of money, you find out that I have $5. Well, you have to know that student A has $5. And if we both have $5, then student B also has $5. So that's the best analogy I can give you. But hopefully we understand. All right, moving down the page. We have our first proof. Now this stuff over here, I wrote that in. That is a little word bank. Now we're going one for one here, meaning there are 5 blanks. There are 5 options. I'm not adding any extra yet because I want you guys to get comfortable doing the proof. It's sort of kind of out of nowhere, I guess is the best way to put it. Okay, so example 1 completed the 2-column proof. So they give us that QT is congruent to RV. So QT. So I'm going to draw above QT blue. So that's what QT is going to be for us. And then RV, I'm going to draw it below in green because these two overlap. So it makes it a little more difficult to show it that way. So your blue and your green, you can't see the edge of that blue because of the light. Let me see if I can adjust. There you go. Well, you see the light. Sorry, lighting's weird. Sorry. So they want us to prove that QR, so this little guy is congruent to this little guy. So let's get our. So first thing was what they gave us. It's given. All right, number 2 is blank, and the definition of congruence. All right, so I have 2 choices that look like they go over here, this one and this one. I can tell you the definition of congruence. So anytime you have something that's equal, then you go to congruent, or if it's congruent, then you go to equal. So right here, if it's equals, if it's the same 2 letters, like, QV, RV, so they're congruent. If they're congruent, they're also equal. If they're equal, they're also congruent, and that's the definition of congruence. So you're going to use QT is equal to RV. All right, so we can mark that one off. But again, notice, so we have the same letters. One is congruence, one is equal. When you do that, like we did here, and same thing at the bottom, just marking it for you. We'll come back, we'll get to that in just a second, but anytime we go from equals to congruence or congruent equals, it's the definition of congruence. So, all right, number 3, QR plus RV equals QT. So let's look and see what this is. So QR plus RT equals QT. So this little guy plus this bigger guy equal from Q to T. And one thing we saw at the top of the page that if you look back to the top of the page, the postulate 3.9 says segment addition postulate. So we're adding this piece plus this piece. Say I broke this pen, I would have to add the 2 sides of the pen to get the whole pen. So that is that, and then the other side, RT plus TV equals RV. So this piece plus this piece equals the whole green. So this is segment addition. I know we didn't look at our choices and kind of act it out, but I can give you all the reasons as we're talking. So that one's gone. So notice we have, I think we're missing something here. All right, so number 4 is blank blank. Now, I can look here and see that this one is subtraction because it's subtracting RT from both sides. So between here and here, it looks like they combine these because, okay, so QT is one side. It's equal to RV on the other side. You just take the little parentheses out. And if you look over here, QR plus RT, so this equals the other side, this. So it's this equals this. You're basically cutting out the equals this and the equal QT equal RV because you're replacing them. So yeah, QR plus RT equals RT plus TV. And And again, wait a minute. Hold on. Stand by. Stand by. Let's go. Okay. Yeah, and that's my missing word. So we substituted QT is equal to this. So we substituted QT for this here, and the other side RV equals RV. We substituted RV for what it equals. So it's substitution. They do that a little strange. All right, so we had substitution over here that I forgot to write in. My apologies. All right, so we've gotten rid of basically everything but simplify, but let's still go through here. So we normally we'd subtract RT from both sides, but we would write it under it. They're just writing across. So QR plus RT minus RT equals RT plus TV minus RT. So again, the minus RT, that's where your subtraction comes in. All right, so when we do that math, or we either solve or we simplify. We did say solve in class. Either one is fine. You're going to have word banks, so you'll get to choose. But in this case, it's simplify. We simplified this equation to here. Notice the last step went from equals to congruent because we wanted to prove QR was congruent to TV, and that is the definition of congruence. I harp on that because that is something that is in the majority of your proofs are going to have at least one definition of congruence. Okay, moving down to the check. So what I'm doing here, I'm going to give you a second. Go ahead and, if you want to pause here, write down all of these. This is your word bank. Again, it didn't get printed. My apologies. But yeah, so everything down here, these 1, 2, 3, 4, 5, 6, 7. These 7 options go in these 7 blanks. Here's your 2 given statements, and you're trying to prove CD. So I'm going to let you guys do that. If you have any questions, please comment on the video or send me a message in Teams or Focus. Or ask me in class. We're going to actually spend tomorrow working an assignment of just these proofs. So it's very important. Okay, I'm going to flip over. Page 2. Okay, example 2. And I guess, this is only 3 little blanks. Yes, you guys need a word bank, but since I'm explaining, and it looks like, yeah, the one below only has one blank. It's the check. Well, we'll let you handle the check. I'll put some words, a word bank for these two before we turn off here. So, example 2, complete the 2-column proof. So I'm going to go through here and kind of mark things as they say. So R is the midpoint of QS. So this guy R, so he's the midpoint of QS. So if he's the midpoint, that means this side and this side are congruent because it's in the middle, or made 2 equal pieces. It bisected it. All right. Now, T is the midpoint of VS. So T is the midpoint of these guys. So the same thing here. If he's the midpoint, that means each side of him to the end of this line segment is congruent. Okay, let's see. So they want to prove that VS, so the whole line is they're both congruent. So let's see. I see there is a third given. You see they give you the first 2 here, and then they give you the last one. It sets up how they need it to unfold. So R is the midpoint of QS, T is the midpoint of VS. That was our given. So we're here. So our next statement says that QR is congruent to RS. So QR is congruent to RS. So basically, if you mark these things as you read them, you kind of give yourself that answer. So because of this, we know these 2 are congruent. And then it says VT is congruent to TS, so the other side. And why do we know those are, or why do we know that? Why did we mark it? Because it was given, but what did they give us? They gave us that those 2 points were midpoints. So by the definition of a midpoint, midpoint, I know that those two sides are congruent to each other. Then they give us this other given statement that QR is congruent to VT. Okay, what I'm gonna do, and this is not a actual geometry move, so please pardon, but so we don't do confusion, I'm gonna do this above the line. I'm gonna draw what they're saying here. So this other given is gonna be green. So QR, so this little guy, and VT, and this little guy. So, oops, let's see. The light is just not right tonight. All right, you can see it now. But so these two are congruent. That's what that says, and it was given. So next up, so QR was congruent to VT because they told us QR has to be now congruent to TS. So it was congruent to RS. So QR and RS over here, QR and RS, and now QR and VT. So QR and VT. So if these guys are congruent to each other and these guys are congruent to each other, this and this has to be congruent to each other because of the which one is actually, what did we put? Hang on, I'm stuck. Oh, well, actually the transitive and symmetric, I was getting to that, but they're using this here because they're substituting. So we already knew that, so that QR, let's say VS and VT and TS are congruent. So you can interchange those. So that's really what we did. We substituted, because these two guys are congruent, we substituted here. So that's a substitution. All right, oops, and all right, so we got that by substitution. So we're missing a blank here. We've already got, so again, these two are congruent, these two are congruent, these two are congruent. What do we have left? It's, so we've talked about everything but, oh, symmetric. So that's, hold on. We can write it the same way. 2 plus 1 equals 3. I mean, sorry, 2 plus 1 equals 3 plus, 2 plus 1 equals 1 plus 2. Sorry. So QR is congruent to TS. TS is also congruent to QR because of the symmetric property of congruence. All right, so we did all those, and then so because QR and TS and QR and all these other guys, now RS and TS, so RS and TS, and the little guys are now congruent because of the transitive, because these two, so now everybody, and that's, sorry, it goes kind of weird like that. Hopefully that helps. Again, reach out to me if you need some help. Down below, the check real quick. Let's see. Let me give you, well, yeah, so we have one statement and 3 of these. So I'm gonna, well, yeah, just read this. That will help you get this over here. Now, if you look up here, you might find the answer to this one. And then down here, you should be able to look at this and not need a word bank, okay? If you can't do it, please reach out to me. But even without a word bank, and I know you're like, man, it sounds like Charlie Brown's mom. It does. Wah, 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 wah. I get it. But do try this for me. Start by marking what they give you. So these two, JG and GI. So I'm just going to color them green. The whole side is congruent to the whole side. So they give you this info. You should be able to mark something for that and something for that. You can mark it all, even though the given, this is the second, never mind, messed up. All right. Just do your best. So down here on example 3. Oops. All right, so Marcellus is planning a birthday party. He measures a length of ribbon for the balloon. Then he uses his ribbon to measure and cut the second ribbon. He continues this pattern until the last ribbon that he cut to measure is the next ribbon. And wait a minute. Using the last ribbon that he cut to measure the next ribbon, and until 10 ribbons have been cut for balloons. Sorry, lots of ribbons. If the last ribbon that he cut is the same length, is the last ribbon that he cut the same length as the first, justify in a narrative proof. All right, so they put this down below. Narrative, and this is kind of, they don't touch on it much. It's like a paragraph, but it's a little less. It's a more of an informal proof. So just like up the question up above, it was the transitive property, and that's what happens here. So because the first is congruent to the second, and the second is congruent to the third, and the third is congruent to the fourth, and the fourth is congruent to the fifth. So first, congruent, second, congruent, third, congruent, fourth, congruent, 10th. So by the transitive property, if these two are congruent, these two would be congruent, these two, all, and 1 and 10. So it's the transitive property, and that's a really much a better way of explaining that. The check over here. So read it. If I'm gonna not write anything, this is a bonus if you're listening. So basically, two of these folks, Maria's 11 inches shorter than her sister, and Luna's 11 inches shorter than her brother. They're asking, so if Maria was shorter than Luna, how would the heights of the two, Clara and Chad, compare? What can be concluded if they were the same height? So the same height part's easy. If both those girls are 11 inches shorter than their siblings are the same height, then they would have to be the same height. The difference part, if so and so's taller, then the other would be taller, the one that correlates with it. But I'm gonna let you guys write that down. It'll be a little paragraph, kind of like that. All right, scooching down to finish this off. So a 2-column proof is an example of a formal proof. Our proofs used to make logical arguments in geometry. That is one for you to answer. And if you have any questions, please let me know. Until next time, have a good night.